Another very special case for the nucleophilic addition towards a carbonyl component is the so-called Wittig reaction. And this is actually a very flexible method to change a carbonyl component into an alkene component. And here you can use a lot of different organic rests at your two starting materials to produce basically very complex alkene components. Let's have a look at the reaction. We are having here at the top, we are having our carbonyl component again. In this case, it's an aldehyde component. And then we are using this specially designed Wittig ylide that we can add to this carbonyl component. We have here a negatively charged carbon atom. This would like to attack here this positively charged carbon atom in our carbonyl component. And we also have a positively charged phosphorus component here that will enact in the next step of the reaction. So our electron density from our carb-N ion attacks here at our carbonyl component. The electron density from the pi bond goes to the oxygen atom, and then we end up with something like this. That's called a beta-ene structure, and we have a negatively charged oxygen atom here and a positively charged phosphorus atom in direct vicinity to each other. So what they want to do is the oxygen acts as an the phosphorus acts as an intramolecular electrophile, so there's a new oxygen phosphorus bond formed, and we end up with this four-membered intermediate state. This is very important. This is the transition state for the Wittig reaction here, and now we have formed a carbon-carbon bond between our former carbonyl component here on the right side in this picture and our former Wittig ylide on the other side of the reaction. And now we have a very strong driving force that this intermediate rearranges, and that's the formation of a phosphorus-oxygen bond. Phosphorus always wants to have access to oxygen in a way, so that's why it's also super easily burns, and why you most of the time in nature find phosphate. The phosphorus is surrounded by 4 oxygen atoms, and in this case, the electron density again rearranges. So one of these sigma bonds gets drawn into and forms a new phosphorus-oxygen double bond, where the other electron density here goes in here and then forms our alkene component. And in the end, what we are left with is the triphenyl phosphine oxide. So again this very thermodynamically strong phosphorus-oxygen bond. And on the other side, we are left with our alkene component. And this is now a very nice way, because this reaction is very flexible to to accept a lot of organic rests that you can attach here. So you can use a wide variety of carbonyl components, but also a lot of components starting from this Wittig ylide that can give you access to a lot of nice structures in a way. And there's also, to no surprise, this was actually the first reaction that could synthetically produce a beta-carotene that we have seen in an earlier lecture from other starting materials. And actually the development of the Wittig reaction was one of the key steps here, and it also yielded the Nobel Prize to Wittig, who invented this reaction, as you can see from the name. The only question that remains is now, how can you synthesize this Wittig ylide that now seems to do like all the heavy lifting in this reaction here? And we can see that here at the bottom of the slide. So we are actually using triphenyl phosphine here. So this is a phosphorus atom with 3 phenyl groups attached. It has a lone pair. It's quite similar to, for example, ammonia. And this then reacts with an alcohol, with a halogen alkane component in an SN2 reaction that we have also seen earlier. The electron density from the phosphorus attacks here. Phosphorus-carbon bond is formed. Phosphorus is positively charged. The bromide leaves, just as in the normal reaction mechanism for the SN2 reaction. And then a base comes by, abstracts one of the protons here. HBr is eliminated, and then we are forming this ylide. And why is it called an ylide structure? We are having these 2 components, yl, from this structure here, where we have like a carbon-phosphorus double bond, and then we have the ete structure here, indicating charged structures here, where we have a positively charged phosphorus atom and this negatively charged carbon atom with the lone pair that was then used in the initial Wittig reaction to react with our carbonyl component. So quite interesting and synthetically very valuable method to produce alkanes.